This is CORDIScovery. Hello and welcome to this episode of CORDIScovery with me, Abigail Acton. Europe, home to historic buildings and winding medieval streets, our architecture is frequently very picturesque, but much of our building stock predates current ambitious energy efficiency requirements. Just heating and cooling houses generates 36% of our total emissions. Buildings are the single largest source of energy consumption in the EU, responsible for around 40% of energy consumption and 36% of the energy-related greenhouse gas emissions. On the other hand, we need more houses. According to Eurostat in 2022, over 16% of people living in the EU were in overcrowded houses. So how do we balance our need for more buildings while reducing the environmental impact of the construction sector? What's the latest in the world of passive cooling and heating? Can we make our buildings more resilient to natural disasters? And can innovative approaches to 3D printing have far-reaching impacts? Perhaps our three guests, all of whom received EU funding for scientific research, have some answers. With us today is Abdelghani Meslem, Senior Research Engineer in Hazard and Risk Modelling at NORSAR. He is also Associate Professor in Structural Dynamics at the Norwegian University of Life Sciences, NMBU. His work is focused on earthquake disaster risk modelling, risk reduction and management. Hello, Abdelghani.
Hello, hi.
Paweł Sikora is Associate Professor at the Faculty of Civil and Environmental Engineering of West Pomeranian University of Technology in Poland. His main research areas of interest are additive manufacturing, lightweight concretes, and nanotechnology. Hello, Paweł.
Hi, hello, everybody.
Andrzej Lubczyk is Assistant Professor of Nanotechnologies and Nanomaterials at the Research Centre in Industrial Engineering, Management and Sustainability, which is part of Lisbon University. Andrzej, who co-founded the Deep Tech Lab, is focused on harnessing nanoengineering to generate renewable energy. Hi, Andrzej.
Hello, Abigail. Thank you for the introduction. Thank you for having me here.
It's a great pleasure to have you. Okay, I'm going to turn to Abdelghani. From analysing the ability of materials to withstand an earthquake to disaster management after one, the Turnkey project looked at the resilience of our urban environments. So, Abdelghani, when you first considered the resilience of the built environment in different countries, what was your key finding?
Yes, thank you for this question. Actually, our investigation has shown clearly that resilience can be influenced by three main factors. The first one is the construction technology and the practice in use. This includes, of course, building materials regulation. The second factor was policies and legislations for the construction sector. In some countries, for instance, to get a permit for constructing private houses does not require to go through a technical control agency. Municipality will take care of this, which is basically will reduce the resilience. The other factor, which is more related to the cultural and social dimension. So for the very first part or first factor, there has been a number of innovation, such as having new material with high performance structural connection using new technology for connecting structures, sensors that control the overall behavior, and we can get out of it the level of ductility, which express the level of which a given building can go beyond a certain level of deformation without having serious damage.
Okay, and so when you talk about novel approaches, new innovative approaches to making these buildings more resilient, can you be more precise? What sort of things? So yes, increasing the ductility, the ability for a building to absorb stress. How is that done?
Okay, so what we have done is we have first, one part of the work, we have developed the new sensors. Those sensors can monitor the structural health condition of a given buildings. Especially when we are talking about critical buildings such as hospitals, schools. So we can use this kind of information to detect any kind of changes in material characteristics, especially the stiffness. Stiffness is the DNA of a given buildings. And then we can, from there, predict what is the expected behavior. And then we can work and identify the weaknesses and work on providing solution to improve the resilience. So this is...
Okay, great. So when you're talking about a novel type of sensor, what makes these sensors new and where do you place them?
So in the past, most of the sensors are conventional sensors, very heavy sensors, expensive sensors that use very specific data, and usually it's only used for very, very much specific infrastructures or network. Now we can use, for example, a smartphone-based sensors that has capability to accept a different type of information, that we managed to develop a framework that can harmonize those data and then come up with an easy to read information.
So what kind of data then? So you were talking about rigidity and, of course, stiffness, which then, of course, makes a building less able to deal with stress. But so what are you looking at? Because presumably if there's too much flexibility, that makes the building not particularly reliable either. So what's the sweet point here?
So the data that we collect they are frequency information, frequency content of a given building, so that identify the stiffness, but also the deformations, because we have different types of sensors. So then from those deformations, we can basically predict what will be the behavior, what will be the main weaknesses of a given building at any level. We can put them, and this is the innovative things, very cheap sensors that can be used even in private houses.
Excellent. That's wonderful. So that gives people a real insight into the structural integrity of a building before a quake, I imagine, or is it also information coming shortly after?
The aim is, as I said, the title of our project is toward more earthquake resilience urban society. It means that before earthquake can be used, those information, we can already predict what's going to happen and work to reduce vulnerability and hence increase resilience.
Brilliant.
But of course, it can be used after an earthquake to already localize the most affected area. So, for example, we have sensors in given region. We can simulate all buildings that are same typology will suffer the same thing. Then the disaster management authority already knows where to focus the search, especially when we talk about critical infrastructures or critical buildings like school, hospitals.
And power stations, I imagine, and things like that.
Yeah.
Yeah. Okay, great. So it shows where the potential damage can be, and then it enables authorities to take steps prior and more quickly after. Okay, that's fantastic. Thank you very much. So these ground motion models are real time. So who is actually using this information? It's I think gathered together in a platform in the cloud, is it? How does that part work?
So the platform we developed can be used by two parties. The scientists, but the disaster management authorities. And this is the key factor of the project, is we produce something that can be used not just for scientists. So we generate those maps, we improve the way how it generates, how it can update few seconds later, so that already authorities know where the intensity is higher, and they already know where are the most vulnerable zones. So then they know where to focus, because this is the key point in disaster management. I have seen it many times that authorities, they have no idea where to go, where to start from, but the tools shows where to start from.
Excellent. This is fantastic work, and I can imagine it's life-saving. So, but what attracted you to this area of research in the first place, Abdelghani?
Yeah, I come from Algeria. So in 2003, there was a huge earthquake, which caused 23,000 deaths, plus more than 100,000 building collapsed. At that time, I was master's student, about to finish, and so I have seen with my eyes, actually, how these three factors that I just mentioned, the regulation, legislation, the lack of legislation and regulations, and also the lack of understanding from the general public, because earthquake doesn't kill. People kill themselves.
Right.
If you follow the rules, it should work. It always worked in Japan. It should work somewhere else. So it's all about education. And of course, provide authorities with the tools that can help them, because this is also another issue that we have observed.
Right. I suppose when it comes to enforcing legislation, which on the ground might seem unnecessarily cumbersome, if you've got the data to prove how important it is to adhere to that, then people are more prepared.
Yes. We use this information from the disaster. Then we tell them, look, these are the condition under which a disaster happened. So if you improve this point and this, it should increase the resilience and reduce the vulnerability.
Excellent. And unfortunately, if you're in a seismic zone, you can be pretty sure that it won't just be one earthquake. There might be another one coming. So you learn.
Always.
Yeah, indeed. Okay, that was fantastic. Thank you so much. How interesting. Does anyone have any questions or observations for Abdelghani? Yeah, Andre, what would you like to ask or say?
Yeah, thank you. I'm very curious to know because I'm very far from what you are doing. So your detector is supposed to be very sensitive, right? And for the big cities, is there any interference of these signals by vibrations and anything related to the movement of the transportations or whatsoever? Is there any limitations?
Obviously, yes, because when you put sensors, the first things you work with is filtering. So you need to filter all unwanted noise. So definitely you have to do that. But now this was a problem with the old sensors, which has less capability in frequency range. But now I think with all these new sensors, they are quite very high resolutions, so that you can very easily remove all the unwanted noise. So yeah.
Yeah, that's a very good point, because the houses shake something quite dramatically when trams pass by.
Yeah, and we are talking about frequency. Frequency means we already know what is the range of frequency of interest of a given building, house. So any high frequency that you see, it has nothing to do with the building. So it must be something else. So you already know your range of frequency of interest.
Excellent. Yes, Paweł.
So I believe there's some kind of, you can use some modeling to see which part of the building is the most stressed.
Exactly.
And then you can kind of locate the sensors there, right? Is it?
Yeah, this is the aim actually. Is, the more you put a sensor, the best is your model, because sensors help you to calibrate your numerical model. And then from there, we can actually predict reality, how the building is going to behave, and then you can already know all the frequency levels, how it changed, the deformation shape, and then from there you get the stiffness. Then you can know already the weaknesses of a given building, and then you can work on it to improve the resilience.
Excellent. Thank you so much. And actually, Paweł, I'm going to turn to you right now, because talking about resilient buildings, I mean, the building materials themselves are obviously of interest here. So you're looking at something very intriguing. 3D printing is always interesting, and its application in the Ultralight Con 3D project was particularly so. The project looked at ways of printing walls. Now, I don't know, but to me that sounds absolutely fascinating. Tell us more. What exactly did you set out to do, Paweł?
Thank you for this question. So, let's start from the history. If we think about construction industry, we try to solve modern problems with old technologies. So we use this old technologies of building brick by brick, putting elements, by elements, and it didn't change over thousands of years, right? And if we think about the printing, we watch this, science fiction movies. We would like to print our house. We'd like to make them, the machine will do it for us, right? We watch the Jetsons movie, and these houses looks very fancy and sophisticated. And that's what actually 3D printing is. It allows us to decrease the labor. In the simplest way, to draw something in the computer, click it on the computer, and then print it out.
It sounds fantastic, but obviously there's quite a few steps to actually get from the concept to the reality. So how do you actually go about printing a wall? Tell us, bring it to life for us. What does the inside of your workspace look like?
Yeah, so in the simplest way, I think to imagine how the 3D printing process looks like, we can actually think about the devices which we use nowadays, like a CNC cutting machine, right? So it's basically a gantry element, a thing which is moving. So if we have a thing which can move in the X, Y, and Z axis, we can call it a 3D printer in the simplest way, right? And then if we have a hose and the pump, we can connect it with this gantry, and write the script on the computer, make it move, and we put through the pump, through the hose, we put the concrete, and basically that's how the printer works. And this is, let's say, the simplest explanation.
Okay, then that's great, and that helps. But I'm just thinking myself, icing a cake using a nozzle, and I can make an enormous amount of mess just doing that. So I'm trying to work out, when you've got liquid coming out of the hose, I mean, how do you prevent it? It must be of a certain consistency, I suppose, to stop it just running everywhere. What do you just? Is it like thick paste, and you just build up layer on layer on layer?
That's actually where all the fun starts.
I bet. I can imagine.
If we think about concrete, and the concrete was designed to be flowable, like conventional concrete should flow. But in 3D printing, we have to kind of redesign the concept of concrete. So if we try to think about this is more like a stiff material, which is extrudable. So it contains cement and the binder phase, but it is much more sticky. So what we would like to have, what is the principles of design of this material? We would like to have a material which is flowable during the pumping process, but it should be stable after the deposition. And I don't want to go into to complicated technological aspects, but we call this the characteristics of this material of such material is, we call it a thixotropic behavior. So we need a thixotropic material. This allows us to extrude the material and make it stable after the deposition.
That's fantastic. Thank you. And we always love new words on CORDIscovery, so that's fine. Excellent. Okay. Now, tell me a little bit about what you discovered about using glass, because this, I think, is wonderful.
So yeah, in construction industry, we have or in general in our life, we have a lot of waste produced, right? And the glass is the most popular material we have everywhere. And as we know, we throw it away very often. We move it. We give it to recycling. But recycling is a great idea, but you never get this 100% recycling rate, right? And this is the same story happens with glass. The finer the particles of glass, the more difficult it is to recycle them because of the impurities, because we cannot guess, the quality and so on. So the finer fraction, let's say below 2 millimeters, 4 millimeters, they are hardly recycled. So we have to find some solution. Generally, they are just landfilled, right? So we have to find solution. And this is when concrete comes, where the civil engineering comes. The concrete can, well, in a simple way, accept all of the waste. So we can solidify using the cement, all the waste into, let's say, so-called artificial stone, right? And we have a strong potential to recycle the glass, because if we think about glass, it's basically a combination of sand and the other components, right? So we are kind of recycling the material which is coming out from the sand, right? So that's what we found out, that this could be a great solution to deal with the problem of landfilling the fine particles of glass.
And what I think is particularly cool from a previous conversation we shared is that not only are you returning the glass to be used in the same way as sand is used to make the glass in the first place, so that's very elegant, but you've also found that it has thermal properties, haven't you?
Yes, exactly. Due to the production process, the atomic structure of the glass is a little bit different comparing to the one of the sand. I will not go into too many details because
Sure.
this is the chemical aspects. But the outcome of this is due to the production of the glass, we get a material with substantially lower thermal conductivity. So comparing to the natural sand, the recycled glass has a lower thermal conductivity. That's mean if we use it, we can produce, let's say, insulating building materials or benefit from the low thermal conductivity by decreasing the thermal conductivity of the produced concrete.
It's wonderful. It's so neat. Excellent, excellent. Okay. And where could these walls be used, whether the walls or the technology behind the walls? Where do you see 3D printing for construction purposes taking us, Paweł, if we were to go into really blue sky thinking?
Yeah, so basically everywhere. I mean, we are facing the problem of the labor. We're facing the problem in the construction market of the very short construction times. 3D printing helps us to solve some of these problems. So basically, the 3D printing can be used for the common housing, for the basic houses. It can be used for the prefabrication, so production of the offsite production. That means you can have a hall where you produce some prefabricated elements, which can be used later on. I don't know, prefabricated balconies, for instance, right? So this can be done offsite. So these are the, let's say, most common application.
I did read a while back, we're talking about offsite, very definitely very offsite, the notion of using 3D printing for constructing basic buildings or building materials on the moon, for example, using dust, sintering dust.
Definitely. So this is one of the fields where 3D printing has, it's a sophisticated technology. So thinking about using it in the lunar application, this is a great idea. I mean, we have a problem with the oxygen availability there and so on and so on. So we need devices, we need machines which can produce the shelters for us, right? If we would like to move there eventually someday. So the 3D printing could be the great solution.
Right, has great potential for that sort of thing as well. Yeah, wonderful. That sounds fantastic, doesn't it? Does anyone have any comments for Paweł? Thank you very much, Paweł. That was beautifully explained. Anyone got any questions? Yes, Andrei, what would you like to ask?
Thank you. First of all, Paweł, great project. Very innovative idea. I enjoy a lot. So, but as for non-professional, could you just please explain? So, in terms of the production speed or building speed of this type of wall, I mean, how it will looks like, maybe let's fix it like 10 per 10 meters, for example, wall.
Right. So I will just give you the example. The simple structure, like 2 by 2 by 2. So like a small big building, we can print it, let's say, in 6 hours, 8 hours. So this is the time frame, right?
Isn't that amazing?
That's incredible. Yeah.
That's very fun, isn't it? Isn't that wonderful?
Also, could you please explain how these affect the energy efficiency of the buildings? Because, you mentioned one very important parameters, which is the insulation, right? But what about thermal mass or some others which can also affect the energy efficiency?
This is actually the core of my project, and thank you for asking that. So if you produce the standard concrete wall, like the monolithic wall, you have it filled by concrete, right? So if you use the formwork, which is a steel form, you have to pour the concrete inside, right? So you will have a solid element. The 3D printing, the great characteristic of 3D printing is that we can design our own printing path. So you can use topology design to print, let's say, hollow elements inside with some infill, and we can fill it with the infill insulating material. And that was the part of the great part of my project, to use the 3D printing, let's say, only to print the load-bearing, the structural element, very thin element. So inside, we can put any insulating material we would like to have. I mean, the best would be something which is working well with concrete, so having the same, characteristics. But you can put lightweight concrete. You can put some lightweight aggregates inside. You can put polyurethane foam, so you can kind of control the insulating characteristics of the wall.
Okay, super. Well, thank you very much. I'm going to turn to Andre now. Andre, your project, the SHARE project with 2 S's, came up with a very clever idea to heat and cool buildings using zero energy. And we all know just how impactful on the climate that is. So that would be wonderful if we can do it. So we've been exploring the idea of insulation using recycled glass, but yours exploits something less tangible, the moisture in the air around us. So this is a fascinating proposition. How did you come to think of it?
Well, I was postdoc and we were working on another project, which was air purification from airborne viruses and bacteria. And we're supposed to develop material that would provide reactive species by interacting with atmospheric oxygen. And these species would kill the airborne viruses and bacteria. And so during the electrical measurements, we find out that the results were interfered by something. And as we found later, it was a breathing of the experimentator. And so since that time, we started to explore the process, and we found out that it was actually humidity, atmospheric humidity, that interacting with material can make electrical signal, which is voltage and the current. So this is how the everything started. And we was very, very skeptical in the beginning. We had the first funding for the proof of concept for this idea. We went well, but among us, I was not the most skeptical guy in the lab who were doing this. Was one in 4 years after the first project ended, he said, listen, I find out that probably this, even with low power generation, can be used for the construction materials, because construction materials requires a lot of material there, and this was the beginning to find a application for this idea of energy generation from atmospheric humidity.
Right, lovely. So you had a researcher who noticed that their own act of breathing was causing a transitional change in the material that they were working with. I think that's fascinating. So you are looking at, if we stick to the thermoregulation concept, you're looking at ways of heating and cooling buildings passively. So can you tell us actually how this works?
Sure, absolutely. So for SHARE project, there's a combination of 2 technologies. It's the radiant heating and cooling system, and the second one is the converter of atmospheric humidity into electrical energy. The first one is in order to imagine it simple, it's the silicate-based plate, inside which you have tubes. So by passing the water through these tubes, you can cool, if the water is hot or cold, you can cool down or warm up the surrounding atmosphere inside the building. So this system is usually attached to the ceiling or the walls of the building, and it's more efficient than the regular air conditioning systems. because partially these tubes has holes, so the water can come out inside of silicate materials, which has a huge absorption capacity towards water. So this 10 kilogram silicate plate can absorb 20 kilogram of water. And then it's imitate perspiration of our body. So when it's hot outside, it's release the water and cool down the atmosphere, and vice versa. So the system can both work absorption and desorption to heat and cool down the building.
That's wonderful. Where does the water come from, Andre?
So it was any source of water. You have to dig into the water, you use a pump, and this is where we came with our technology. So this was exactly an idea to supply this system and make it self-sufficient. So we use the same humidity, not only to heat and cool the building, but also to supply the pump to make the water flowing inside those tubes.
Okay. And is it a closed loop system so that you just supply some water and then it takes care of itself? I mean, you're losing some to evaporation, obviously. So presumably you need to add water. How does that work?
So the pump is installed somewhere, and it's taking the water from the source outside of the building.
And pumping it through these panels. Yeah. And how big are these panels, Andre? Are we talking about the size of a wall, or are we talking about sort of the size of a radiator? Or
so the system been installed to our partners. It was 144 square meters. Facilities, ceiling. Of course, we were not that time. We were not by the end of the project. We didn't manage to cover it entirely with with our system. But we made a 1 square meter panel combining both technologies. So our panel was installed under the top of their panel, and it was hidden under the clays and layers of everything. So it looks like a regular room, but it was self-sufficient in terms of the air conditioning.
That's really interesting, and it sounds like an excellent solution. Obviously, much less environmental impact than things like air conditioning and so on. But you're mentioning the notion of 2 panels here, Andre. So we've got the silicate panel with the tubes that have water going through and little holes that let the water out, and as you described, then act like perspiration. But you're talking about a second panel. What is this second panel?
Well, the second panel is exactly our technology. We were developing on converting atmospheric humidity into electrical energy. So we use the humidity that is outgoing and the water outgoing of the silicate panel, and for generation of the electrical energy to supply the water pump. So our panel is way thinner. It's like only a few millimeters. But of the same surface area as the silicate panel, in order to cover the full surface area.
So, if I understand you correctly, you can, by having the panel that collects the electricity, you can actually get enough electricity to power the pump.
Well, from just one panel, one square meter, no. So we need several, because the efficiency of this process is quite low. The source energy is quite low. We are dealing with the diffusion, and it's way less energetic than the solar energy or wind energy. Nevertheless, since we have humidity everywhere continuously.
Right. So they might not be very powerful, but it's totally continuous. So it's sort of always dripping away, as it were. And so if you had panels that were really the size of a wall or something like that, and you had this very thin panel behind it collecting the electricity, then eventually you should have something that's self-powering, yes?
Yes, exactly. So this is our target. First of all, since very, very beginning, our main target was improvement of the conversion efficiency. Currently, it's around 1% only. So, but despite it sounds very small, we already can think about the real scale application, because we can provide enough energy to supply many things. So we have that project ongoing. And within this project, we are focused only on the technology the standalone solution that will provide household with the amount of energy that it can cover its electrical energy needs. So this would be a 1 cubic meter device that provide 10 kilowatt hours of electrical energy per day.
And all just from the idea of the humidity?
Yes, just atmospheric humidity. So standalone solution in line with the others like solars and the wind. So we are proposing a new source of renewable energy.
That's fascinating.
And yeah, there is a wide range of application. And personally, I believe that the building and construction is the future for us as well.
Okay, that's brilliant. Yes, because you have the scale. Yeah. No, that's super. Thank you very much. That's a fascinating concept. Does anyone have any observations or comments to make to Andre? Yeah, Paweł.
So I have a question. Is this technology can replace air conditioning, or it can facilitate or decrease the let's say, the consumption of energy by air conditioning? This is the first question. So maybe you can firstly reply to the first one.
Yeah. So I think it's more complex than air conditioning because it needs to be integrated when you start building, your building your construction, physically, because air conditioning you can install later any moment. It's required less time. So, but it's more efficient. So it's probably good for the new buildings.
And could it replace air conditioning? That was the question.
Yes, of course, absolutely. So we make some measurements. We can on Mallorca, where we perform the test. The guys perform the test because it's this part is their technology. Our part is only atmospheric humidity converter. So they were able to maintain constant temperature during an entire year for this building with almost no consumption of the energy.
Fantastic. Excellent.
I would like to ask also about some theoretical limitation of this system. I mean, maybe in some climate when it's too dry or it's too humid, it's not applicable. Do you have any limitation for this technology, or it's only for intermediate zones, or it can be used everywhere?
Yeah. So this is a very good question. Well, in fact, it works from 20% of relative humidity to 100%. The higher humidity, the better. Of course, the more current can be get out of this conversion process, but it will fit for all European countries, because not many people know, but the average humidity per each European country is almost 70%. So, which is good for us. Yeah.
Wow. Okay. That was an excellent question. Yes, that's true, isn't it? If you're depending on something being, a certain degree of humidity, you wonder what would happen if it got too dry. Does all the panels just dry out? Yeah. No, apparently not. They don't.
No, but we can feel it with water, so.
Yes, indeed. Yeah.
And it will work again.
With your self-feeding pump. Yeah, excellent. Well, listen, thank you so much. I really enjoyed that. This is, you shared some really valuable insights into the development of the innovations with the construction industry. I think it was Paweł who pointed out that, the construction sector has really had a bit of a technology bypass for quite a few hundred years. I think that was your phrase, wasn't it? I like it. I'm stealing it. So it's wonderful to see new concepts coming down the line. Thank you so much for your time.
Thank you very much, Abigail. Bye-bye.
Thank you very much.
Thank you very much.
Bye.
Thank you. Bye-bye.
Bye-bye. You're very welcome. Goodbye, everyone. If you've enjoyed this podcast, follow us on Spotify and Apple Podcasts or wherever else you are listening to your podcasts. Check out the homepage on the Cordis website and subscribe to make sure that the hottest research in EU-funded science isn't passing you by. And if you are enjoying listening, why not spread the word? We've talked about how gravity might impact our microbiomes, and we've looked at how artificial intelligence can help bees thrive. In our last 36 episodes, there'll be something there to tweak your curiosity. Perhaps you want to know what other EU-funded projects are doing to make the construction sector greener and more efficient. On the Cordis website, you'll find information on projects working in this area, including a collection of projects under the title Old Meets Green, New Technologies to Retrofit Buildings in Europe. The website has articles and interviews that explore the results of research being conducted in a very broad range of domains and subjects, from ecography to echolocation. There's something there for you. So come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line, editorial@cordis.europa.eu. Until next time.